Welcome back. Our topic now is moving away from our quantitative work on solutions and acids and all those kind of things into more of an introduction to an element on the periodic table that's one of our favorite elements, and that element right there is carbon. And what's so special about carbon? It turns out when you're a chemistry major, you're going to take two classes, 2 whole semesters, 1 year of courses that are around the chemistry of carbon. And then you're going to take 1 semester, half a year, of courses that cover pretty much the rest of the periodic table. So there's something really, really important about carbon. And many of you know that carbon is the basis for life as we know it, our DNA. Most of our cell structures are made up of carbon attached to hydrogen, nitrogen, oxygen, and a few other things here and there. And it's amazing. It's amazing the chemistry that carbon can do. But what is it about carbon that makes it have all those special properties? Well, primarily it's 2 things. One, it can make a lot of bonds. You think of carbon, it's got 4 valence electrons, which means it can make 4 bonds. 1, 2, 3, 4 bonds to other things, or 2 bonds to other atoms and a double bond to one atom, or triple bonds. It can do all sorts of really interesting chemistry. The other really neat thing about carbon is it's very predictable. Silicon also makes 4 bonds, but it's not the basis of any life forms that we know of. And that's because it can do some chemistry that carbon can't do that's a little less predictable, a little more variable, and we don't want that in life. In life, you want to be able to predict things and know that when you attach this to this, it's always going to attach in exactly the same way, and carbon can do that. And so that's why we are carbon-based life forms. So when you study things that are based on carbon, you're studying what's called organic chemistry. It's the study of things that are made primarily of carbon, hydrogen, and oxygen. So that's kind of our first definition. It is the study of molecules primarily made of carbon. That is what organic chemistry is. And when we talk about organic molecules, we're going to talk about molecules that are primarily carbon, hydrogen, oxygen, maybe some nitrogen, and we'll see some other things as we go through this section of the class. And so one thing we have to do is start talking about naming. Obviously, whenever we go to a new thing, we're going to talk about how we name them. But we're also going to talk about how we draw them, because these things that we call hydrocarbons, those are molecules primarily made of carbon and hydrogen. They get pretty big pretty fast, and if we continue to draw them in our more traditional Lewis structure format, it gets really tedious, as you'll see in the next slide. So let's start with the most simple hydrocarbon that there is. 1 carbon atom. And if you remember, how do we make a carbon atom happy with hydrogens? Is you end up with CH4. Carbon with 4 hydrogens, CH4. Never 3, because then carbon wouldn't be happy. And we call this methane. Methane is the first hydrocarbon. Now, if we go to the next one, a little more complicated, we have 2 carbons. How do we make each of those carbons happy? Well, we know carbon likes to make 4 bonds. We've got 1 bond drawn between them, and so there's going to be 3 other bonds here in order to make that carbon happy. 3 other bonds to make this carbon happy. And it looks something like that, and we get a formula of C2H6. And this one is called ethane. And you'll notice that A and E ending, tells us we have a hydrocarbon that is made up of single bonds only and no double bonded carbons. Keep going. We go to C3. And again, how do we make each of these happy? Well, we figured out that N1 needs 3 hydrogens. What about this middle one? How many hydrogens does it need to be happy? Well, if you see, it's already got 1, 2 bonds drawn away from it. And so it only needs 2 more bonds. And luckily on our Lewis structure, that's just what fits anyway. And we draw these hydrogens 3 on the end one to make him happy. Everybody's got 8 electrons. We call this C3H8, and some of you might know this. This is propane. This is what you're going to buy in the gas cylinders for your grill and things like that. Keep going. C4H. Oh, look at all those H's. H, 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 H. Anybody else getting tired of drawing H's? Yeah, I'm so getting tired of drawing H's. And this isn't even a very large hydrocarbon. What happens when you get C10, C20, C30, C100? What happens when you get DNA? You can't just keep drawing these things the same way. This one is C4H10, and you might know it better as what's in a lighter of butane. And again, that A on E ending saying all those carbons are single bonded to each other. All right, so we decide we can't keep drawing things like this. These are what are called expanded structures. Expanded structures are essentially Lewis structures. They show everything connected to everything else. But there's a couple other structures that people draw in order to save themselves a little bit of time. So let me label this one as an expanded structure. People will also draw what's called a condensed structure. And a condensed structure primarily focuses on groups. And you can see we've kind of got this group here that's CH3 on the end. Then there's a group next to it that's CH2, a group next to it that's CH2, and a group next to that one that is CH3. And you see we can just kind of put each group there. And you have to know a little bit about chemistry, because if you look at this, it almost looks like that H3 is attached to a carbon on either side, but we know that hydrogen can only make one bond, so it can't be in the middle. You can't have CHC like that, because that would be hydrogen having 2 bonds. And so we have to know a little bit of chemistry when we use this format to know that those carbons are the things that are bonded together, not the hydrogens. This is called a condensed structure. And it certainly makes things a little bit easier. We could do it for propane. It would be CH3, CH2, CH3 like that. Makes things faster. But how could we make it even faster? And what I'm going to do is I'm going to draw the answer first. You're going to look at it, wonder how that's the same thing, and then I'm going to explain it to you. We're going to use what's called a skeletal structure. And a skeletal structure just says, hey, look, if we know we're drawing things that are primarily made of carbon and hydrogen, we can leave off a lot of the details and fill those in later with our brains if we need to. And I'm going to draw butane looking like that. Up, down, up. How can that be butane? How can that be the same thing as the thing I drew? Well, it turns out when you're drawing these condensed structures, these skeletal structures, there's a few rules. An unlabeled endpoint, I'm going to circle all my unlabeled endpoints here, is always carbon. So each one of those is a carbon even though it's not labeled. And so we have 4 carbons in here for those 4 circles that I drew. So we still have C4. Now, what about our hydrogens? Well, if there's nothing drawn, we know that carbon always forms 4 bonds. So right now, this carbon that I circled on the left, it's got 1 bond drawn to the thing next to it, but it needs 3 more bonds to be happy. And we know that those are going to be hydrogens, because that's what this kind of system does. So there's 3 hydrogens on this one. This one, you can see there's 2 bonds drawn away from it. So it's got 2, it needs 2 more. So there's 2 hydrogens on that guy to make him happy. This one, same, 2 bonds drawn, so 2 more to make him happy. This one has 1 bond drawn away from him, and so he needs 3 more hydrogens to make him happy. And if you add that up, 3, 4, 5, 6, 7, 8, 9, 10, you get C4H10, the same formula that we had when we drew out our expanded structure or our condensed structure. And you can see a skeletal structure takes a fraction of a second to draw, right? If I'm not very neat about it, I can draw it really, really quickly. And so it's really what chemists use when they're drawing organic molecules, is the skeletal structure is used 99% of the time. The skeletal structure also allows for flexibility. If you want to focus on one part of the molecule, you can draw a skeletal structure that looks like this. And what happens there? Well, as soon as you label an endpoint, it's not a carbon with an unknown number of hydrogens anymore. It's exactly what you label it. So I labeled it CH3. Now that didn't change from what it was before, because it was a CH3, and now it's still a CH3. But we can do that. We can expand on the structure, draw parts of it expanded, parts of it skeletal, and it allows us to do a lot of organic molecules very, very quickly. So it is a very commonly used feature. All right, so let's go back up here. We're going to add a column, and we're going to draw skeletal structures. We just did butane. It looks like that. Propane's got 3 carbons, so it looks like that. Ready? 1, 2, 3 carbons. How many hydrogens on this middle carbon? Hopefully you came up with 2 hydrogens and 3 on each end one, right? Just to make sure there's 4 bonds to every carbon. You don't write those on there normally. I'm just writing there to show you. Ethane. What's a skeletal structure for ethane look like? Well, it looks like that. And because it looks kind of like a line, which looks kind of like a bond, people don't use it very often. So normally if people are going to do ethane, they're going to write out C2H6 or something like that. Methane's even worse. It's actually technically a dot. Nobody uses a dot for methane. They're going to write out CH4. So we don't generally use skeletal structures for methane or ethane, but beyond that we use skeletal structures like crazy. All right, so we got now to C4. Let's go to C5. And C5 is going to end up with H12. 5, if you remember what a 5-sided shape is, it's a pentagon. And so this is pentane. Now, how do we draw the skeletal formula for pentane? Every time I draw a skeletal formula, when I put my pen down, I say a number 1 in my head. And then as I draw a line, when I get to an end, I count up 2, 3. So I'm going to put my pen down and say 1, and then I'm going to go up 2, down 3, up 4, down 5. And you can check your work. 1, 2, 3, 4, 5 endpoints. Oops, it erased everything, so let me do that again. 5 endpoints on there. And so you can see that we have drawn pentane. How many hydrogens on this guy? Hopefully you came up with 2 because he's got 2 bonds drawn, which means there's 2 bonds that are not drawn. C6, H14. A 6-sided shape is a hexagon, and so this is hexane. And we go 1, 2, 3, 4, 5, 6. Okay. I always draw up first instead of down first, but you can draw it 1, 2, 3, 4, 5, 6, just like that. It's exactly the same. It doesn't mean anything different. I just prefer the first one, and I just try to be consistent when I do it, but don't worry about which way you want to do it, whatever way works for you. C7, H16 is going to be heptane. And we draw it by putting our pen down 1, 2, 3, 4, 5, 6, 7. And so you can see, if I had to draw that with all the carbons, all the hydrogens, it would take me an amazing amount of time, especially if I had to draw it several times if I was talking about it. But if I draw it just with a skeletal structure, it's very, very quick. C8, H18. This you might hear at your gas station, octane. Right? When you buy gas, you pay for these different octane ratings, and what you're paying for is the amount of molecules that contain 8 carbon atoms in them. 1, 2, 3, 4, 5, 6, 7, 8. Octane looks something like that. C9H20. My favorite one is nonane. It just sounds so silly. 9 carbons, so I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see I'm having to draw them a little bit smaller now because they're longer molecules. We're going to stop at 10. Certainly the world goes well beyond 10, but we're going to stop at 10. 10 years is a decade, and 10 carbons is a decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks something like that. I got a little bit sloppy at the end, but you can see. Just up, down, up, down, up, down. Now, you might be asking, well, why do you do that up, down, up, down, up, down, Professor Clements? Why not do it some other way? Well, it turns out that because carbon, when you attach 4 things to it, is tetrahedral, it looks something like this. And so you've got carbon, 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 and what is it doing? It's going up, down, up, down. And that's the natural tetrahedral shape for a bunch of carbons in a row. And that's why we draw that as up, down, up, down, up, down, because that's actually the shape it takes on in the world. So you need to be familiar with these because we're going to name molecules using them. So methane all the way up to decane, kind of need to be able to draw those out quickly so that we can name molecules with them later. So those are what we call the alkanes. And I normally have people memorize them in a face-to-face class. In an online class, you have your notes available to you, and so you can use them that way. I know it's unfair, but that's just how it goes. All right. So let's just practice this again. I encourage you to read this prompt. Give a formula, a structural formula, condensed formula. A structural formula is the same as the expanded, or the Lewis structure. A condensed structural formula and a skeletal formula for pentane. Pentagon, pent 5. Okay. So pause, go ahead and do that. And now you're back. So I'm going to start with the skeletal structure because that's the easiest to draw. 1, 2, 3, 4, 5. Then I'm going to write my condensed structure because I'm going to do each one of these one at a time. I know that's a carbon with 3 hydrogens because there's only 1 bond drawn away from him. I know that's a carbon with 2 hydrogens because he's got 2 bonds. Then the next 2 are the same. They've got 2 bonds and 2 bonds, and then the end one is the same as the other end one. And now I've got C5H, and I can just count up. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12 for pentane. So that's how we can draw these skeletal structures and how we can count hydrogens on there. I was just basically adding up on each one of these how many hydrogens there were in order to figure out what was going on and what my chemical formula was. So you can do that for even larger molecules. So this is a very large molecule. How can we figure out how many carbon atoms and hydrogen atoms are in this one? Well, all we got to do is count our unlabeled endpoints. So I'm going to start circling those. 1, 2, 3, 4, 5, 6, 7, 8. Are we done? No, there's 2 endpoints I didn't circle. 9, 10. So we know this has a formula of C10. Now I'm going to erase all my circles. And I'm going to now figure out how many hydrogens I have. 3 on this end one, because there's only 1 bond drawn. 2, 2, 2. What about this one? How many hydrogens on that carbon atom? Well, you can see there's 3 bonds drawn away from it, which means there's only 1 bond that is missing. Same for this guy. 1 bond is missing. 2, 3, 3, 3. And I just add all those up, and what would I get is C10H22. Okay. Is this decane then? No, because decane requires 10 carbons in a row. This has 10 carbons total, but not 10 carbons in a row, and we'll see what this one is called later. If you want to know now, it's actually 3,4-dimethyl octane. But don't worry, you'll actually be able to do that not too long from now. So your turn. You're going to look at this molecule. I'm going to blow it up for you. And you're going to try to figure out how many hydrogen atoms are in this structure. So again, pause, look at this guy, and tell me how many hydrogen atoms are in this structure. All right, you're back. What did you come up with? Well, hopefully you started counting, and endpoints are nice and easy. Endpoints are always 3. This guy is going to be 2 because there's 2 bonds drawn. This is 1, 2, 1, 2. If you add all that up, you get 22, and we have a formula of C10H22. But boy, does that molecule look different than the one we had before in the previous slide and the one we had earlier that we called decane. So it turns out we have lots of different molecules with the same chemical formula that look very different. And it turns out their chemical properties would be very different as well. And we'll talk about that more going on. So far we've drawn all of our things straight in a row. But it turns out molecules with carbon in them and other molecules can make rings as well. They can make kind of circular type structures. And what's the smallest number of carbons you'd need to make a ring? Well, 1 won't do it. 2 won't make a ring. It just makes a line. But if I had 3 and I made a triangle, I could totally make a ring. In fact, that is the smallest ring hydrocarbon. Now, for a ring, the formula is going to be a little bit different. I've still got C3, but now I've only got 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here for a total of 6. And that's very different than our formula of propane that we got before, which was C3H8. Right? So how do we name this one? Well, we name this one the same way we'd name propane. We just put the word cyclo in front to say that it's a ring, and we call this cyclopropane. Remember, the prop just tells me that I have 3 carbons. So the cyclo says I have a ring, prop says I have 3 carbons, and the ane says they're all single bonded. The box molecule, C4H8, what do you think that's going to be called? Well, if you remember, C4 was butane, and so this is going to be called cyclobutane. How about C5? C5H10 cyclopentane. And last, we're going to do this guy. This is C6H12, and it is cyclohexane. Now, we can draw more. There's cyclos that are bigger than this. I stop at these two because these two are very important cyclical molecules in chemistry. We're going to see them all over the place, especially in biological systems. You see cyclohexane and cyclopentane type rings, sometimes with double bonds and things like that. But rings of 5, rings of 6 are very common in biological systems. So if you're naming something with a ring, all you do is count the carbons. You get your methane, ethane, propane, butane, etc. And then you put the cyclo in front to tell someone it's a ring. So here's an example. This is the molecule cholesterol. So you go out, you get yourself a nice burger and fries, and what are you putting in? You're putting in lots of cholesterol into your body, and this is the format of it. But you can see ring of 6, ring of 6, ring of 6, 3 rings of 6. Also, ring of 5. And you can see the person who drew this one, I didn't draw this one, I got this one from elsewhere, used the skeletal formula, but also specifically put in some hydrogens, and that's okay. We learned that in the skeletal formula you can explicitly say some things that you wanted to. We also have something new here, which is something other than carbon and hydrogen, and there's an OH, and we'll talk about those going on. But again, we've got an unlabeled endpoint, and so that O just becomes O, because once you label it, it becomes what you label. So those are our simple alkanes and also our cycloalkanes, the things that have a ring. We now know how to name those, and what we're going to do moving forward is we're going to make it a little more complicated. Is what happens when we start branching off, when instead of just having our pentane, we have pentane with something sticking off of it, and we'll figure out how to name that moving forward. Thanks.